Okay, so welcome once again. So today I'm going to discuss on human-like cognition. So what it is, of course, the context is that we have gathered um, to prepare for the hackathon as part of the conference that is happening in IIT Delhi on 11th of April, called Unriddling the Inference from Pramāṇa Theory to Modern Logic and AI. So the hackathon is part of that, and there will be also poster competitions and conference as usual would have invited talks. So I encourage all of you to participate in this very informative sessions in the conference. So this hackathon or the posters, they are just to prepare for the conference, and you can also encourage your friends, colleagues to participate. So thank you. So let me begin the discussion. So it would be more of an interactive discussion. So I humbly request your active participation. So I see already only 12 participants. So apart from me and Ms. Shruti, there are only 10 participants. So I request your kind attention and participation. So what do you see here? So anybody can speak up.
Duck's beak.
Okay, ducks, beaks. Okay, anything else do you see? Yeah, there are some chats I see. Rabbit. Pallavi is saying duck and rabbit. Yes, correct. This is a classic duck and rabbit ambiguity. So some see is at as duck, some see it as a rabbit. So this is the beak of the duck, and if you want to see a rabbit, so this is the rabbit. This is the face of the rabbit. This is the eye of the rabbit, and these are the ears. So the same figure, the stimulus hasn't changed, but the mind processes information ambiguously. Sometimes you see it as duck, and sometimes you see it as rabbit. So you don't see them as together, duck and rabbit together. You don't see that. Once you see this, the other one collapses. If you see the rabbit, the duck look collapses. So it keeps flipping as you keep watching. So it flips. Similarly, what do you see here?
Two faces or a container, as in a
Okay.
lamp.
Yeah. So yeah, a glass or container or two faces. How many of you see two faces? Yeah, Pallavi also sees. Yeah, who else sees the two faces? Could you recognize the two faces? Yes. Okay. So this is one face, and this is another face. So if you look at the black side, if you focus on the white side, so this is the vessel or cup. So here, what do you see? Can any of you infer what it is? Cyclist. Okay. Anything else? Aesthetic street lamps, but not clear. Okay. Anything else? Blurred lights. Okay. Okay. Anybody else? Final. Okay. So to me also, it appears some blurred image. It looks like some cyclists are cycling. It's a street and lit up, and the image is purposefully made blurred. And there is also one person probably here walking on the road. These are the three cyclists. It looks like that. So the essential point is, so the amount of information here is very less, but yet the brain is able to recognize the cognition that is happening within us. We can picturize a fully blown image of the cyclist or the person walking or street lamps, because those impressions are already there within our cognition, within our memory. somewhere before we have seen those images, or we can project them in this case and infer that yes, this could be the case. So essentially our cognition functions with it can function well with the ambiguities and different possibilities that that is presented before us, and they can be seen in terms of superposition. Say, I give you one example. So say another example, you have a blurry object at night. You saw that from a distance. um, the possibility one that could come to your mind is that it's a dog. Maybe it has appeared in the shape of a dog. So possibility two is that it's a shadow or a bag. So the brain doesn't immediately collapse to one of the interpretations. It tolerates the uncertainty until more information arrives. So in the duck and rabbit illusion can be seen, it's like either as a duck or rabbit, the stimulus remains identical, but the perception alternates. So these are all based on our previous impressions that is stored. So that acts as an additional factor of information. But in this case, when the image is blurred, unless and until we have extra information or previous exposure, so the inference is not happening. So the essential point that I want to make is the cognitive significance is that humans operate effectively, reasonably well under incomplete information also. So that is sometimes termed as some sort of superposition of mental states. So I'm sure all of you must have heard about quantum mechanics. It talks about superposition of states. Multiple things can coexist together. Something similar is happening. Humans maintain multiple interpretations simultaneously when information is incomplete, and collapsing to only one when decision is made. So some sort of superposition. So there are many literature people have explored on this. So, and the second one, the first one I talked about is operation even during ambiguity. So cognition can operate in ambiguity also, as considering different possibilities as superpositions. So then the next one is belief revision, means also called as non-monotonic reasoning. Means human reasoning is non-monotonic, means conclusion can change when new information arrives. For example, suppose you visit a doctor and you have fever and cough. So doctor identifies the pattern and says that, say, this is some, say, disease A. And now you tested the lab, say for example during the COVID time, you had positive COVID-19 report. So seeing that report, the new information has arrived. So the doctor concludes that no, this is not plain cough and cold. This is COVID-19. So so we we as human beings, we have this ability of revising the belief. The earlier conclusion can be withdrawn and replaced by a diagnosis that fits the total evidence. But this is not the way classical logic works, rule-based logic. So I'm not talking about current AI frameworks. The simple rule-based logic, classical logic, Boolean algebra. So you had one if-then statement, and once you had inferred that this is true, but that cannot be changed. So the conclusion cannot be changed unless you either revise the if then statements, the or you with the given set of things, you don't really conclude the different. So it remains the same. If you change the if then statements, have this new evidence also included, then only you can infer correctly. But in the human case, it has the ability of probabilistic reasoning. So, I mean, in the sense that we can conjecture things, we can imagine things, create new things, so and infer based on that. So our human cognition is it doesn't follow the monotonic reasoning. So it is non-monotonic in nature. It it has the ability of updating its own belief. So that's the second point. So let's see one example, another such example. So in case of social logic, say for example, you are standing and one of your colleagues just passed by, and he didn't smile at you. So immediately, what did you infer? You inferred that maybe he's angry with me. That's the initial inference, and he's stubborn and whatnot. You made some inference out of it, and then later on, you learned from somebody else that that particular colleague had received some bad news, and because of that, he was distracted. So your perception changed. So there is a rapid belief revision. So your interpretation shifts from they're angry to maybe he was so preoccupied that he couldn't respond to me. So that is not possible in the classical logic case. So once you have a given model of if then the rule-based symbolic logic, so classical logic, so there is no way of updating such beliefs, but human cognition has this ability of updating the belief. So you need a non-classical framework, um, which is not simple rule-based things. So that is very clear nowadays with the advancement of AI systems. And then the next one I want to talk about is mm, something, yeah, something called order effect. So let's have a description A. You read it out. Intelligent. The person is intelligent, industrious, impulsive, critical, stubborn, and envious. So how much rating would you like to give this person from 1 to 10? Yeah, anybody? Okay, 5. 5. Can't give. Okay, but yeah, at least give something. So okay, so then I ask you another set of description. Read the description B. Envious, stubborn, critical, impulsive, industrious, intelligent. So, and how much rate would you give to this person? Yeah, still 5. Okay. Maybe I disclose the thing beforehand. So, but still, do you feel the difference? Uh, when you started looking at the profile, seeing that intelligent, industrious, impulsive, critical, stubborn, and envious, your perception about the person, and in this case, description B, the order of the qualities are the same, but the order is different. So, thus, it has been seen in psychological experiments statistically in larger population samples that yes, so the order actually matters. So, although there is no logic that they should matter, because if you consider them as a set, so this is the same set as this. So there should be no way that they should appear different. But if you read this order and this order, at least to me, it appears different, and also to many people, and it has been statistically seen in experiments. So this is called technically order effect of human cognition. Suppose I ask you a question. So, do you approve of Prime Minister's economic policy? I ask you the question first, and then I ask you, do you trust the Prime Minister? And just simulate this experiment and ask the question first, do you trust the Prime Minister? And then once the person has answered, then you ask the question, maybe, do you really approve the Prime Minister's economic policy? So the responses in both these cases you would find different. The approval that you will receive, they would be mostly statistical if you measure, you will see a difference. So the issue is when the order flips, although the set wise they are the same. I mean, these are the same two questions, but when asked in a different order, the responses you receive, they are different. So the reason is, so the first question activates certain considerations in memory, and the second judgment then draws on that activated information. So that is the difference, the order effect. And say I ask you, if I give you the statement that patients are given two treatment options, and they first hear. In one case, there is 90% survival rate. And what would happen? You would say that yes, they would form a positive interpretation out of it. And for the latter, you hear that there is a 10% mortality rate. Although both are the same thing, but they appear very different. So, thus, so the way we ask the questions, the way we give a context, that changes our decisions and changes our cognition. So context is very important in the case of cognition. So if at all we want to design an artificial system, it has to have all these different kinds of features. Say, I give you one more familiar example. So suppose actual temperature of an object is 20 degrees Celsius, and in situation A, you step outside after being in a warm room, 28 degree. What you would feel? You feel that the object is cold. And in the situation B, you actually were in a cold room, 12 degrees centigrade, and when you touch that object of 20 degree, what you would feel? You will feel it warm, although the object is the same 20 degree. So our judgment, our cognition depends on prior context. So our cognition is contextual. So what do we learn till now? Our cognition is contextual. Our cognition follows order effects. Our cognition is able to process ambiguous informations by making superposition of mental states. So these may appear very trivial examples to some of you, and you may be thinking, what is there here to learn? So these meta principles are very important. Oftentimes they're neglected. So when we want to simulate any artificial systems, we need to really bother about these fundamental questions. Say I give you one more familiar example. So suppose you earn 80,000 rupees per month, and all your friends earn 40,000. So what you would feel? That my salary is good. And in the context B, all your colleagues earn 2 lakhs a month per month, and what you would feel? Yeah, my salary is very low. So the objective salary didn't change, but the evaluation pattern changed because the social context has changed. So the phenomenon is very widely known in social comparison theories. So the point is, context matter a lot. So suppose you are given a dessert and you eat it after very spicy food. The dessert would taste extremely sweet. And you eat it after another sweet dessert, you'll feel less sweet. So the perception now depends on the contrast with previous stimuli. So order also matters, the context also matters. Same for exam difficulty, for example. You have context A, you solve 3 very difficult problems and then encounter a moderately difficult one. What you would feel? This question is very easy, damn easy. Suppose in context B, you solve 3 easy problems and then all of a sudden you encounter a difficult one. What you would feel? This question is very hard. So although that difficult question could be the same, but because the context has changed, the perception of that object has also changed. So the question didn't change, but the difficulty of judgment is now contextualized. So when we want to simulate the decision making of an artificial agent, so this contextuality needs to be taken care of. So yeah, so in human cognition, the stimuli are not interpreted independently. So meaning is constructed related to surrounding information. So judgments, they really depend on previous stimuli, social comparison, situational framing, conversational context, and like that. So all these different contexts modulate our decision making. So this contextual dependence is why cognitive scientists argue that human reasoning cannot be fully modeled by context-independent classical systems. So what does that mean? So it means, so classical system means something that operates at the level of classical probability. So I'll come to that. What is classical probability? So classical probability means it follows the Bayesian statistics, means the laws of total probability. So you have a prior, you have a posterior, and you measure the probability through that, and you make the update in the probabilities. So yeah, and they strictly operate in the principle of Boolean logic. So of course, classical probability can work independent of Boolean logic also, in terms of uh, real numbers also, real continuous numbers. So that's also a possibility. The essential point is the classical probability has been seen as a marker of rationality, as a marker of a normative experience. Means this is the normal, this is the norm of the thing. So what we call normal is mostly we mean classical probability. But human cognition has been seen to violate all of these principles. So thus, human cognition is not cannot be properly modeled using classical probabilities, whether it is Bayesian or any such variants that we know. So theory of mind, this is another important thing. So when you want to represent others' belief, say a child hides a chocolate in a drawer, and the mother moves it to fridge when the child is not looking at it, and later the child returns. So this is the statement. So you predict. So when the child returns, what would you predict? So you would predict that the child will look into the drawer. Why? Because you understand that the child's belief, even though you know real locations. So since the child has hidden it inside the drawer, so there are the most likely chance that you will predict that um, it is in the drawer. So when you want to represent others' belief, so this is one important aspect. So and say I'm giving you some practical examples so that you can appreciate these abstract ideas. So, so there is this principle of heuristics, means our brain, our cognition process, it finds fast mental shortcuts. So, I give you some example. This also goes by the name availability bias. So suppose you saw some recent news that the airplane has crashed. Say, for example, recently the Ahmedabad accident that happened. So, and when someone you watch this television or internet clip, uh, and then someone asks you, which is more dangerous, plane travel or car travel? And many people would say it's plane travel, even though the statistics shows that cars are much more dangerous, they're prone to accidents than the aircrafts. But since we have been exposed to this particular clip news, people become fearful. So I would tell you one funny story. The day this crash happened, the next day I was flying in Air India. Next day morning, so so I could see the passengers so panicked, so I mean so distressed. They're patiently hearing, very carefully hearing the crew members' address. So so that shows, although the statistically we know that if you follow the classical statistics or whatever, so we know that the statistics of plane crash is low, but since this immediate thing has happened, So that influences our decision making, cognition. So we tend to think that plane is more dangerous than car. So there is another important factor called conjunction fallacy, also that violates the classical probability. Say I have a description that Rahul is very concerned about environmental issues and participates in climate protest. That's a description prior given. So which of these two statements appear more probable? So Rahul is a bank employee, or Rahul is a bank employee and environmental activist. So which one would you choose? So yeah, mostly people would choose B because logically probability of two things happening together cannot exceed the probability of one thing alone. So in terms of classical probability, so people choose B because it fits the description better. So that's the bias that influences. So all these different things need to be modeled when we really bother about artificial cognition. There are much more also, but essentially these are the prominent ones. The feature and the core ideas, let me list. So ambiguity tolerance, yes, multiple interpretations are maintained within the cognition. The human brain, or human cognition, it is capable of belief revision. The effect of contextuality plays a very important role. The order effects is very important. When you represent others' belief, so yeah, so you have to, consider those effects when you represent others' belief system. So it's not what you consider as norm or the conclusion or the decision should be. It's rather their belief influences the outcome of the decision or the inference. Heuristic. Our mind finds mental shortcuts, and the important one is conjunction fallacy, that it violates the classical probability. In conjunction, when it happens, one appears more probable than other, although both could be at the same probability level. So essentially I made you go through all this to drive one point at home, is that the empirical findings in human cognition and decision making, so they violate the classical probability rules. So what is classical probability? Classical probability means, so it's only that you don't know the exact nature, it's your ignorance that is being modeled. So let me give you one small example. So when you toss a coin, so it's actually starting from the tip of your fingers. As it lands on ground, you can exactly follow the trajectory if you know the air pressure, the temperature, the if any wind is blowing. So if you know all environmental factors, you can exactly predict what the outcome is going to come. There is no probability here, absolutely certainty. So it's only that you don't know what the environmental factors are there. So thus you tend to say that yes, there is 50% probability of head, 50% probability of tail. And similarly for any other scenario. So classical probability is essentially a model of our ignorance. But there are other variants, say for example quantum mechanics, the way it operates. So there is, the quantum probabilities are not like that. They are quite ontological in the nature, in the sense that you just cannot predict what is going to happen. It will completely uncaused. There is no reason why this happened. You cannot say why the wave function collapsed to, say, an electron is in plus half state. That is what you observed. You don't know before experiment, before you made the measurement, that whether it is to be measured at plus half or minus half spin. So it's only when the observer comes into the place I mean, observer means here the detector, a general notion of detector, not a sentient being necessarily. So when the measurement was made, so it was concluded that yes, so this is the state. So once that state has collapsed, it would continue to stay in that particular state. So that is very different from classical probability. So that is called quantum probability, and also that is also an example of non-classical probability. So our human cognition is not a classical system. Classical, it doesn't follow classical statistics. So essentially, it has to be non-classical. So thus, it has been seen that quantum formalism, they model it very well. So essentially, what I'm going to conclude is that if at all we want to model it, so quantum formalism is a very powerful framework to model it. Of course, you can go to any other frameworks, logical systems. There are many different sets. Even in other traditions, for example, in Jñāna tradition, there are sevenfold logical frameworks. Even in our modern science also, there are starting from fuzzy logic to many other logical frameworks. So you can do any such methods, but they have some nuances, some issues. They may model one aspect of cognition better. They may leave out some other aspects of cognition. So that is something we need to really bother about. So once we know what we are modeling, so that aspect would be very clear. So till now I have been talking about classical probability, Boolean logic. So what does that really mean? So just to give you some understanding. So the core of Boolean logic is there are two values, truth values that you have, 1 and 0. So 1 is considered true and say 0 is considered false. And what are the core logical operations? You have conjunction, which is equivalent to set theory and you have disjunction or you have negation or not. So if you construct a truth table, so say statement x and y, so they are 0 0 means and would give 0 or would give 0. So 0 and 1 you get and 0 or as 1. So if you change them, then it's still 1. When you have both true, so both and or both gives 1. So in summary, so this truth table, when you work in terms of sets means it has to be a discrete one mostly. So here in this case, that is how you know by the name event space. So how many outcomes that is there, so possibilities, that's a full event space. And then you have certain outcomes, that is A, and certain outcome B and certain outcome C. So the rule of distributivity follows. So the whole of Boolean logic, if you are operating at the set theory level, you can describe like this, that it should follow the distributivity. So, and then, yeah, of course, when you map them into as sets, so the logical constructions and or and not, they would translate as the and would translate as intersection, means I want this and this. Say I want something from A and something from B. So that means something in common would be something in common between A and B is what I am interested in. So that is the intersection part. And or say I want A or B. So that means both together. That's a union. And complement rule means anything other than A, that is a complement. That is the Boolean not operator. So now once you map that to sets, so you have the choice of something called measures. Measures means you assign a numeric value to your sets, say outcomes A. So that is what known by the name probability. It comes under the measure theory. So if somebody is interested, they can go in details. So you have sample space, say omega. That is what the total probability is. That is 1. Because if if you say total probability is greater than 1, so it doesn't make much sense. So in this case, probability theory, you assign total probability of 1. So thus, since A is a subset of the total space, so the P of A, the probability of A cannot be 1. At max it can 1, so it cannot exceed 1. So it has to be greater than 0, but less than 1. So this is one condition also that gets violated in the case of human cognitive systems. It has been seen. So it also follows the additivity, means when you have union, so it is essentially P of A plus P of B, and it is also it can also be translated to something called total probability. What is the probability of B? That P of A and P of B given that A has occurred. So in terms of conditional probability, you can express them. So the essential point is our normative standard of rationality is mostly by classical probability. So anything that doesn't follow classical probability, we term that as irrational behavior. But it is not really irrational. It is actually the feature of human cognition. That is something we need to bother about if we want to model human cognition. So sometimes this forms as a Boolean case, that is called. So each event is independent, so there is no overlap among them. So and that is how it is very plainly represented as a grid, or any such array you make, any such memory allocations you make, any such storage you make. So essentially you are talking about a Boolean kind of framework. So there is no overlap of two events. So and thus say I say this let me have a ledger pointer. So suppose you say this is my A. So anything other than A means all this would be negation of A. So it very neatly partitions. So that's why the law of total probability holds, and that is how your normal conception also works. If I eat this much portion of a cake, so this much portion of cake would be remaining. So that is the usual classical notion of understanding the reality, or that is the classical notion of cognition that we understand. So it has been seen human cognition doesn't follow this rule. It violates the law of total probability. So is it clear till now, or it's becoming abstract? So any response from the participants? Okay, so yes.
The last couple of slides, they have become slightly abstract. Before that, it was very.
Yeah, that was the beginning, just to get you started. The initial slides, the purpose was to motivate different features of cognition, like we discussed contextuality, that how context matters in terms of cognition, how order effects matter, how conjunction effects matter. So essentially, I listed different features of cognition, and which we need to bother about when we consider artificial systems. If we want to represent all of this uh, in artificial systems, then we need to care about them. So essentially, if I want human-like cognition in artificial systems, my artificial system should also display all these characters. So,
Mhm.
so that is the point. So and now I'm jumping to the fact that what can be the very minimal logical framework in which our computational tools operate. So
Yeah.
that is the classical probability. And
Yeah.
classical probability, when translates into our electronics and digital electronics,
Mm.
essentially we talk about Boolean logic.
Yeah. Yeah.
So, and Boolean logic leads to classical probability, and classical probability is something that human cognition disobeys. So till now, that's the message.
Hmm.
So okay, so is it clear now?
Yeah.
Okay, thank you. So, and then as we have seen empirically in different cognitive science experiments, that there is an empirical bridge, means the law of total probability, or as I said, if the intersection i- is certainly is a subset of A, right? So A intersection B means this is always a subset of A, but it has been seen that it doesn't really follow the rule that the probability associated with this part would be less than this part. So this is signature of non-classicality. So the crisis is that the rationality is not to be equated with the Boolean kind of structure. So instead of considering such behavior as irrational, we should consider them as a feature of cognition. So that's the essential point. So to do that, I'll give you some examples in real life scenarios which I myself have tried. So in this particular paper, I tried to model the cognition of birds, the flocking behavior particularly. Flocking means they form beautiful, spectacular patterns as they move around. They make a very coordinated motions, like the birds here, the starlings motion, or the fish swarm, or even drone swarm. So all these multi-agent systems, so here they are living multi-agent systems. Multi-agent, it could be any other multi-agent system also. So it's a generic notion. And every multi-agent system has some perception mechanism, some attention mechanism, some decision-making modules. So it works with that principle. Now, so here in this case, what we showed is that we modeled the decision-making of these agents in terms of quantum formalism, quantum logic, which is essentially non-classical logic. So when we did that, so usually the motion of these birds, or the patterns they form, they are predicted by some nonlinear dynamical models, classical nonlinear dynamical model, heuristic models. But we cast that as a problem in cognition, related to cognition. So what we did is we modeled only the perceptual part here. Say each A is representing one agent here. Say A1, A2, A3, A4, A5, A6, like that are many. Each A is a bird here. Now I simplify the situation. I say that this is the bird's vision cone, means this is the domain of its perception, and this much ability of perception it has. It could be abstracted to any other multi-agent system with a similar notion that this is the set of neighbors it can interact with. Say they are two in number. Now the bird has the ambiguity, like in the beginning I said human cognition can handle ambiguity as superposition kind of states. So here the decision to follow this or this can be superimposed. So I represent the perception of perceptual decision making uh, of each of these neighbor in terms of a quantum state. Means I say that 1 means to follow, 0 means to not follow. So, and there can be ambiguity that I'm really following or not following. So this can be represented as a superposition of these states. And then I have another agent. So something similar for it also. And then I can make a product state, means as a joint state, which could be again the language of entanglement can also be brought in. Even simple separable states can be separable, means my decision about A2 is independent of A3, or I'm not very clear about there was one level of ambiguity at the A2 level or A3 level. There is another level of ambiguity that I don't know whether I'm following A2 or A3. So that is also possible. So all of this can be represented as different quantum like states. So once I do that, So I have the behavior of the birds very nicely coming out. The physical motions, then I make a correspondence. I define what does it mean to perceive the world out there. Say you have many boats, they are making some decisions and inferring something. They have certain neighborhood, and they can accordingly can frame what does it mean to perceive for each of these boats. So it can be abstracted to any sophistication. So once I do that, I get wonderful patterns like it used to be predicted in classical nonlinear dynamical models. Uh, and then there is another aspect that I very silently ignored. Here I just bother about the neighbors. But what about myself? That I know that I am observing the other neighbors. So this aspect of metacognition is a second order effect. Our even our Nyaya Sutras, Nyaya text. So what does it say? It says first the perception will happen, and then perception about oneself. That yes, I am observing the object. So that's a second order effect. So like here the boy is looking at the red sky. So it is seeing the red sky. So at the same time, after the red sky is seen, it also knows that I am seeing the red sky. Means there are two aspects: the self and the object of perception. So the person is aware of both his or her self and also the external world. So this is a more difficult problem than here. So here the agent is only aware of its surrounding, its neighborhood. But here the agent is not only aware of the surrounding, the neighborhood, but also aware of the own self. So that is called metacognition. It's a second order effect, and yeah, as per Nyaya tradition, also, and also in modern understandings also. So the self part is a slow part. So even some recent developments in logical frameworks, so they consider such aspects of metacognition. They're increasingly considering the aspects. So if I want to represent cognition artificially, I need to bother about the perceptual decision making, means the objects of perception. At the same time, the self part also, that the self is aware of its own self. So the recursion kind of. So I become the object of myself. So, and once I introduce this aspect, the system develops a memory naturally. The self is a slower part, and the perceptual like reflexes or bodily reflexes. So they are a fast system. So once I couple the slow and fast system, so the system naturally gives rise to some kind of memory in the network. So and so this is a very powerful way of representing what it means to have samskaras, means previous impressions, like the kind of scenes we undergo in our life, kind of food that we eat, the kind of company we keep. So all that creates a bias to us, and because of that, our perception and decision making, everything gets modulated. So here in this work, what I did is the self and the perception both are interacting just not with the neighbors but also with the environment. So there is a kind of relaxation means releasing out energy, so or settling to equilibrium states. So once that aspect is seen, so the system yeah, as I said, doesn't follow the usual route of reversibility. Means say like you might have heard about magnetism. When you have a magnetic material and you keep applying external magnetic field, the dipoles get aligned with it, and then it becomes magnetized, and you keep reducing the magnetic field, and you don't see the trajectory following the same direction. So there is a leftover magnetization even if you have reduced the magnetic field to zero. You have to reverse the direction, then only it would come to its original state. So that is called hysteresis in magnetic material. Similar thing is also seen in this model, and also we know from our experience that exposure to stimuli creates bias. It enables learning within us as a prior. So all that gets loaded within our cognitive systems, or antakarana, as our tradition says. That is something we need to bother about. So essentially, I'll not go through these different logical frameworks. So I described the classical logic, which is mostly propositional logic, and there are others, many valued logics like Jñāna system or fuzzy logic, where you have the indeterminacy statement A and not A and in between. So probabilistic logic, Bayesian frameworks, and there are many others. Recent developments are happening around neuro-symbolic integration also. So that is very close to the slow fast system that I described, and it's emerging trend. Many different kinds of neural nets are being developed based on this idea. But what I feel is the quantum inspired logic, dynamical logic. So it's a very powerful framework. It answers the ambiguity and uncertainty tolerance aspect of cognition, belief revision, or the monotonicity of the cognition, contextuality and order effects, the social cognition aspect also. And that is the very closest logical framework one can use to fully dynamically represent the biological cognition. Here I'm not talking about artificial cognition the way we are operating at. I'm saying human-like cognition, which is which may not be as efficient as the ChatGPT or other bots, but uh, it's not good at repetitive things. But it has its own flavor. Means no matter how good the bots are, we know that they are not human. They are not alive. So there is a difference between human agents, and artificial agents. So probably with these quantum inspired frameworks, we can advance the logical framework. So that's the logical framework part. So now let me revisit the Naya inferential framework, which I believe is a different framework, different logical framework, which is not really quantum mechanical, but it is also a non-classical logical framework because of several aspects, particularly something called abhava. Abhava means it's actually the absence of something, like uh, we are experiencing, say, um, you have exposure to certain things. Say you ate a mango yesterday, and today that mango is not there. So, so you can say the experience of the cognition of that mango is abhava, means it's ontologically real. It is not the cognition of that is not really Boolean negation, the not operator, that complementarity that we talked about. It's different. So that aspect needs to be handled very carefully, and several other aspects are also there. So once we take care of all this, and then probably we can come up with a framework where we can have something ready for artificial cognition. Again, these are all very ambitious things. Um, so the purpose of this hackathon or conference is to create some awareness and inspire students and researchers to work on it, so that a systematic logical framework and inference mechanism based on our tradition can be developed. So to repeat the five avayavas that yesterday Dr. Srinivas discussed. So he gave the example of several examples. One of the examples was the smoke and fire example. means there is you saw some smoke billowing out of the mountain, and you inferred that yes, there is some fire on the mountain. So how is that done? So to repeat yesterday's discussion, you have first the statement, the pratigya or the proposition. There is fire on the mountain. The reason is that there is smoke, and you apply a universal rule called Bapti, and that whenever there is fire, there is a smoke. So this universal rule when applied, and you also exemplified through Udaharan that in my kitchen I have seen that, and thus the deterministic logic. Then you apply the application Upanayan, the consideration, the application part. Yes. So thus, so this mountain has smoke. Thus, thus there is fire. So after the Upanay, the ascertainment, the Nishchaya happened. Conclusion, it's called Nigaman, and you conclude that yes, therefore the Hetu means the region, the smoke, and the Sadhya means the fire. So they are mapped by the Bapti. Bapti means the universal principle. Whenever there is smoke, there is fire. So thus the Nishcha, the ascertainment happened. So knowledge then appears as a mental episode, and that's viewed as quality of the Atman produced by the structured causal factors. But Nyaya, it's not a probability of belief. Nyaya talks about the ascertainment of reality. So it's not an epistemic adjustment like the quantum probability, quantum formalism does. It's an epistemic adjustment, adjustment to address the non-classical nature of the cognition. But Nyaya talks about the ontological reality. It talks about complete ascertainment. So it doesn't really talk about the degree of confidence or numerical coherence, means it is 99% correct. So Nyaya doesn't admit that as correct. So Nyaya says if that is the case, then revisit the Bapti, the universal principle that you use to infer the conclusion, and rectify that, then you will come to correct ascertainment. So currently the issue of explainability is a big thing in our AI systems. So we want explainability to morally account for it, or okay. So so Nyaya talks about complete ascertainment of reality. It's not really statistical inference. So whenever we have issue, we need to revisit the Bapti, and yesterday Dr. Srinivas mentioned about Anvaya and Vyatireka. So positive concomitance and negative concomitance. So what does that mean? Say you have this classic example, smoke and fire example. So whenever Anvaya part means whenever you have smoke, there has to be fire. So the kitchen stove, for example, the smoke is present, the fire is present. Campfire, smoke is present, fire is present. Factory chimney, smoke is present, fire is present. The Vyatirek is the negative case. Whenever there is no fire, there should be no smoke. So whenever we need to search for, so essentially when we are talking about artificial cognition to model, so our framework should look for the Baptis. So the representation of Baptis, the universal rules that governs the inference. So essentially it's a search for the universal rule. So whenever there is no fire, there is no smoke. So that's the Vyatirek part. Lake surface, it has no fire, no smoke. Empty sky, no fire, no smoke. No snowfield, no fire, no smoke. So that's the negative part. Suppose I come across wet fuel. So there is no fire, but yet smoke. So how do I handle that? Then I go back and revise my Bapti. I said that whenever there is wet fuel, fire doesn't give rise to smoke. When there is dry fuel, there is fire and there is smoke. So that's the inference mechanism. So essentially it boils down to finding correct Bapti, and probably you have to use some kind of non-classical logic to model it, not necessarily quantum logic. There are many such non-classical aspects, starting from fuzzy logic and other things. So whatever works the best. So we need one epistemic framework, like here, one of the logical frameworks, and then the inference mechanism that we are doing will be looking for a correct Bapti. So for Pramāṇa oriented inference. So that is all that you have to do. So yeah, so these are some of my thoughts. So wish you all the